Let's take a look at this monster of an integral. Or maybe not so much if you use spherical coordinates. So I got everything set up on the screen for you. We have our transformations, what x, y, and z turn to, and what our Jacobian is as well. And we also have this integral with really, really weird bounds. What and how do you even solve this? Okay, let's start off with this. First off, we already see that, oops, quick mistake right here. These bounds just describe a unit ball. Not a unit ball, a ball with bounds radius of 7. And the reason why you can tell that is because this is obviously some function of z, and this function of z is plus or minus, right? And this already just describes a sphere. So as same for the negative part. And our radius is simply just the square root of 49, so we know that this describes a sphere of radius 7. And our integrand is simply 1, so we're just integrating 1. What does that mean? Well, whenever you integrate with 1, so your integrand is 1, you are finding the volume of whatever figure you are integrating over. Same as whenever you are integrating with the function of 1 using double integrals, you're finding an area. So keep that in mind. We are finding the volume of a sphere with radius 7 right now. And let's actually rewrite this entire integral so that it goes with our spherical coordinates. So our radius is 7, right? Phi is maxed out at pi, and theta is maxed out at 2 pi. So this new bounds we wrote just represent our sphere with a radius of 7. If we continue, we have dv. What does dv turn into? Well, dv has a transformation factor, I guess you could say, of rho squared, rho is just p, and sine phi. And the order in which you wrote the bounds, we're integrating with rho first, and then with phi, and then with theta. So this is our new integral, actually. We have our transformation factor set up, p squared sine of phi, and our bounds. And maybe you're asking what happened to our previous function 1. Well, our function was simply just 1 times this, which is the same thing. Now, if our function was x, this would be slightly different. You would be multiplying this entire thing with x. And x transformed into spherical coordinates would be p sine phi cosine theta, multiplied by everything here. But our function isn't x. That was just to cover all bases for understanding for you guys. And all we gotta do is just integrate this like a normal triple integral. So, first things first, we integrate p squared sine of phi with respect to p, or rho, whatever you call it. And this is just power rule. So it's p to the power of 3 times sine of phi. Since phi is being treated as a constant, it's just a coefficient, quote-unquote coefficient in this case, so we just ignore it. Our bounds are equal to p, and we substitute 7 into here. We get 3, let me look at my notes. We get 343 over 3 sine of phi. If you substitute in 0 here, nothing happens. Everything just zeroes out. So this is our new integrand. Now we integrate with respect to phi. So we have 343 over 3 sine of phi d phi. Now that we have this this is just negative 343 over 3 cosine phi. So the integral of 343 over 3 sine of phi is equal to negative 343 over 3 cosine of phi. We set up our bounds. If we plug in pi into here, you get negative 1 into your cosine. So negative 1 times 343 over 3 is just 343 over 3. If we plug in 0, you get 1. So our answer is negative 343 over 3, which is simply minus 343 over 3 equal to 686 over 3. And lastly, we're integrating this over theta. D theta equals 686 theta 2 pi, and 0 are our bounds. And we multiply, and this is basically, these bounds just represent multiplying this by 2 pi. And if you multiply this by 2 pi, you end up getting 1372 pi over 3. And if you just search up volume of a sphere and then plug in the radius of 7, this will be the answer that you get. So that's how you know the answer is right in this case, because of a special property of our integrand being 1. Now this one, slightly trickier, because our integrand is now an actual function of x, y, and z. All of these. But this is actually quite simple, because in spherical coordinates, x, y, z all squared just equal to p squared. And I'll show you that right now. So how will I show you this? Well, I'll actually substitute in all the values for x, y, and z into whatever we have here. You get p cosine theta squared plus p sine phi sine theta squared plus p cosine phi squared. Let's make some more space for this. And if you square all of these, you get p squared sine squared phi cosine squared theta plus, and so on, so on. I'll write everything down for you guys to see. Cosine squared phi. What you can actually do is factor out your p. And you don't have to do this every single time. I'm just writing everything down just so you guys know how this identity, or whatever you call it, comes to be. Or I'll just call it convenient equation, or convenient equality. Cosine squared phi. Now how does this turn into p squared? I'm going to show you. If you factor out a sine phi from everything only in the first two terms of your equation, you end up getting something that looks like this. Cosine squared theta plus sine squared theta. This just equals 1. So we can actually cancel this out. P squared sine squared phi plus cosine squared phi. That's all we're left with. And again, this is the sine squared cosine squared identity, so this equals to 1. And we're left with p squared. So what we actually have here is the integrand of p squared. Let's rewrite our triple integral. P squared dv. Now, the volume that we're integrating over, or the shape we're integrating over, is simply unit ball. So it is a ball with the radius 1, just like a unit circle. Unit circle is just a circle with the radius of 1. So rho would be 1. And our phi and theta values will encompass the entire sphere. So 0 pi and 0 2 pi. Now we have to turn dv into our polar coordinate values, and dv is simply equal to our what this is called a Jacobian. So we have p squared sine phi, our transformation factor, whatever you call it, whatever you like to call it, and our d values are dp, d phi, and d theta, because that's the order we wrote the bounds in. Let me actually simplify this further to get p to the power 4 sine phi. And this is our integral. Now the hard part's over, and we are just doing easy calculus at this point. After setting up your triple integral, which is usually the hard part, it's just make sure you don't make an arithmetic error or some calculus 1 error. So p to the power 4 sine phi dp is equal to p to the power 5 over 5 sine phi. 0 and 1 are equal to p, and all you get is 1 over sine phi once you plug in for 1 and 0. That's our new integrand, so we get pi down here. We integrate what we got previously with respect to phi. What this is just 1 over 5 negative 1 over 5 cosine of phi from 0 to pi. If you plug in for pi here, you get negative 1. And negative 1 times negative 1/5 is just 1/5. If you plug in for 0, you get negative 1/5. So we subtract by negative 1/5, which is simply equal to 2/5. And lastly, we integrate with respect to theta, and since this is just a constant, all we do is multiply 2 over 5 by 2 pi, which is equal to 4 pi over 5. So what we learned from this, keep in mind, x squared plus y squared plus z squared is equal to p squared. If you ever see that and you're integrating with spherical coordinates, turn it into p squared. Super easy. For this next problem, our integram is already in spherical coordinates. We have e to the power of negative p cubed. Now, what's the issue with this? It's slightly harder because of the bounds. Our bounds are x greater than 0, y greater than 0, z is greater than 0. So just the octant, the first octant is our bounds. How do you write the bounds for this? Well, I didn't even know this until ChatGPT told me. But your p bounds will be from 0 to infinity. So we're going to get some type of indefinite integral that we can solve for, of course. But if you don't have any bounds on anything, p is just equal to, or rho is just equal to 0 through infinity. And just saying, your rho value has to always be 0 or some positive number. It cannot be some negative number. So you can't get negative infinity rho, right? Has to be just 0 or positive infinity. Now, what do we do about our phi value? Well, our phi value in the first octant, if you want to cover just the first octant, is just pi over 2, because that's the angle that you make with the z-axis. Phi is the angle rho makes with the z-axis, and pi over 2 seems right. How about for theta? Well, theta in the first octant is again just pi over 2. And remember, theta is the angle that rho makes with the positive x-axis. So now that we have our bounds, we can actually just write them down. 0 and infinity, 0, pi over 2 and 0 pi over 2. And what do we do with the dv? Well, dv, we have to write our transformation factor into here. And let's write all our the d values. Or I think they're called differentials. Doesn't matter. Maybe someone in the comment section will tell me. Now that we have the setup, just integrate. So, e to the negative p3, p squared, sine of phi, with respect to p. Using u substitution, hopefully you know how to use that by now. If you don't, you should watch a video on it. But I'll just show you the integral after this. Using u substitution, your integral ends up being negative 1 over 3 times e to the power of negative p to the power of 3. Now, don't forget about the sine of phi. So our bounds are 0, infinity. And if we plug in for infinity into p, we get, well, 0. Because e over infinity to the power of infinity is just 0, is just infinity, and 1 over infinity is just 0. So everything in this equation turns to 0. What if we plug in for 0 here? Well, 0 to the power of 3, right, is equal to 0. So e to the power of 0 is simply 1. 1 over 1 is just 1. And if we multiply 1 times this entire thing, it stays the same. So what we get is negative 1 over 3 sine of phi, which is just equal to 1 over 3, positive 1 over 3 sine of phi. Now we integrate with respect to phi, and our integrand is 1 over 3 sine of phi d phi. This is equal to negative 1 over 3 cosine of phi, and our bounds are pi over 2 and 0. We plug in pi over 2 here, cosine of pi over 2 is just 0. If we plug in 0 into cosine, we get 1. So 1 times negative 1/3 is just equal to negative 1/3. And this all just comes together to equal 1 over 3. And this is just super simple from here. Because we are integrating with a constant, sorry, our bound is pi over 2. For d theta, we just multiply 1 over 3 by our bounds. But I'm going to write the entire thing for you guys so you can understand. But all this is pi over 2 times 1/3 is just equal to pi over 6. And 0 times that, this right here, is just 0. So our final answer is pi over 6. My golly god. If you've made it this far in the video, you don't have a TikTok attention span. But thankfully, this is the last problem for you guys. I literally just took a break between the last question. I ate a bag of chips and had some dinner. So I am full and stuffed, and I'm ready to answer this last question. Let's do this. Now, we have our bounds. I just gave them to you because by now, hopefully, you understand how the bounds work for spherical coordinates. But all we have to do is substitute for z here. So z is just equal to p cosine of phi, and dv, remember, is equal to p squared sine of phi of d p d phi d theta. Again, doesn't matter which how you integrate, doesn't matter what order. I just prefer integrating with p, phi, and theta first. Our bounds are already given to us, so let's write it all down. Let's clean up our integrand a little bit because we can actually simplify this further. So our integrand is p cubed times sine of phi times cosine of phi, dp d phi d theta. And all we have to do is finish the problem. So let's finish it. 0 and 1, p cubed sine of phi cosine of phi dp is equal to p to the power 4 over 4 sine of phi cosine of phi, with our bounds 0 and 1 for p. And all p is just 1 over 4. If we substitute in 1. For sine phi cosine phi. This is our new integrand, and now we integrate with respect to phi. So we have 1 over 4 sine of phi in our previous problem cosine of phi. And we're integrating with respect to phi. This is just a u sub problem. I'm not going to worry too much about it, but it's just 1 over 4 sine squared of phi over 2. 0 and pi over 3 is equal to phi. And I just use u sub for this. So keep in mind whenever you whenever you find the derivative of this, which should be your integrand, it's equal to this. So the derivative of this function is equal to our integrand. And you can just double check that. You just require some chain rule, some power rule. And all that's left off with after this is 3 over 8 times 1/4. And this is just 3 over 32. Last integral is 0 to 2 pi of 3 over 32 of d theta, which is just equal to 3 over 32 times theta from 0 to 2 pi. And this is simply equal to 3 over 16 pi. So that was it. That was spherical coordinates. I hope this video was helpful, and I try to cover all the bases possible. If you have any questions, put it down in the comment section.